SwayamPrabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We were discussing about miscible displacement. That is, if we have a mixing that is taking place inside a porous medium, because already there is a resident fluid sitting inside the porous medium, and then we are injecting another fluid which can mix with the resident fluid. So, how this mixing takes place? How we can characterize this mixing, or by looking at the signatures at the outlet, what understanding, what inference we can draw about the pore transport inside the transport at pore level inside this porous medium. So, these are some of the things which we are trying to address. So, we started with the definition first, that we started with the case where you have a static pool of liquid in which a drop of ink is placed. So, it has nothing to do with porous medium, and we ended up with an equation. We said we have not given you the derivation as such, but we showed that what are the governing equations we used to arrive at this equation, and we said that this C1 is a function of position and time. So, this gives me, suppose I have, this is my concentration as a function of Z, a one dimensional problem, and if we have a Dirac function, and if we place this inside a beaker full of water. So, this Dirac function will gradually, we will see that this is going to be, this is going to take a shape like this. So, that means this pulse that I have provided here, that is gradually spreading out if we with time. So, now if we place this whole thing inside a porous medium, that means suppose I have a porous, this is the porous medium, and here we introduced a pulse like this. So, that means how we are introducing a pulse? What we are doing here is we are having a flow through this porous medium, continuous flow is going on, injection of fluid is going on. Say, let us say we have water inside this porous medium, and we are also injecting water through the porous medium. And then what we did is, I have a small toggle here and or small port here, through which using an injection syringe we introduced some color in it, or introduced some salt, high concentration of salt in this. For a very short time we injected a pulse. So, this will simulate something similar to a Dirac function. There are two ways we can do this introduction. One is like a pulse like this, or what we can do is we can have two different containers. One container was the simple water that was being injected, and another container is containing the salt. So, this here we have a valve. So, suppose this is the salt and this is the water. So, water was continuously being injected, and this is let us say 1% NaCl solution, 1% NaCl solution, a small amount of salt put in there. So, this, let us say here we have some way to measure this concentration at the outlet. So, we could have introduced it as a pulse. That means, we could have just for a fraction of a second we open this, so that this 1% NaCl solution goes in there, and then again we go back to the to our original water flow. Or we can have it as a step change. That means, the water was flowing in, but then at some point we pull the toggle, and then it is continuously the 1% NaCl would be flowing, not water anymore. That means, we could have given a pulse which is something like this, or we could have given a step change something like this. So, step change we have given in concentration. So, we could see, we expect that this will come out at the outlet at some point. When it will come out at the outlet? Because it has certain amount of residence time inside the fluid. So, it will take some time for this pulse that we have given, or for the step change that we have given, to show that will show up at the outlet after some time. What is that time? Let us say I have a flow rate Q. I am talking about a flow rate Q. So, this entire flow rate is not changed. The flow rate is Q all the time. So, if flow rate is Q, and let us say we have this cross sectional area which is A. So, what is the superficial velocity in that case? Superficial velocity is V superficial in this case is Q divided by A. That is the superficial velocity, right. So, if Q divided by A is the superficial velocity, what is the residence time that the fluid will be in this porous medium? How long it will take for the porous medium to reach the outlet? So, we can think of, let us say this fluid, this porous medium has a porosity of phi, the cross sectional area is A, and let us say this length of the porous medium is L. So, what that means is the volume of this porous medium is A into L. So, volume of this entire medium is A into L. So, if we multiply this with phi, this is the pore volume. So, this is equal to pore volume. So, essentially I expect that if I am injecting at a flow rate of Q, so let us say Q meter cube per second is the unit, Q meter cube per second is the flow rate which we are injecting, and phi into A into L, A is in meter square and L is in meter, phi is dimensionless since its porosity. So, let us say this is in phi into A into L meter cube. So, then how long it takes for the fluid that is injected here to reach the outlet? That would be, if we do this, phi AL is the total void volume, this Q has to travel through this void volume, right. This divided by Q, in that case this numerator is meter cube and the denominator is in meter cube per second. So, this meter cube and meter cube, they will cancel out. So, this second goes to the numerator, right. So, this many seconds would be required for the fluid to reach the outlet. So, phi into A into L divided by Q. So, this I can call the residence time. So, this is the residence time that one must provide. So, after this residence time, I can expect this pulse to show up at the outlet, I mean in a very overall sense. Similarly, if I give a step change, I would see another step change coming at the outlet. So, there must be some kind of detector to measure the concentration. So, after this much of residence time, I expect these pulse or this step change to arrive at the outlet. So, this we must know at the very onset. Now, if this is so, then suppose I have this pulse is in static system and this is the equation that was followed at that time. So, now suppose this pulse, I am introducing this pulse here, I have introduced this pulse here at the inlet and this pulse is traveling to the downstream. So, then I expect that, so essentially I am giving this pulse a residence time of T race, the residence time of T race after which this pulse arrives at the outlet. Okay. So, now if we try to find out what would be the concentration at this, so here let us say this is the this pulse had already, it was a Dirac function here, but it has already diffused like this, just like this. So, let us say it has gone up to this. So, basically you have given this pulse this much of time. So, this is, we said that as time increases, these would be the shape of the pulse. So, after residence, after you have given T race of residence time, this much of residence time, whatever the pulse shape is, had the flow being all in plug flow, that means as if this is just a static system, I am simply traveling it all the way there. So, I am providing as if this is sitting in a beaker and I am providing a residence time. So, over residence time whatever diffusion can take place, it has taken place, and now it has arrived at the outlet with this much, this is the front. So, we can think in that line. Okay. So, if that is so, so if we want to utilize the same equation, one thing is for certain, that this is for a static Z, right, the Z, that this is for a static system. So, that means the Z is always the wherever this the Z is starting from the origin, and that die was placed at the origin. But in this case the Z, we have to see one thing is that the center of this pulse, that is moving, right. So, at any time how much the center of the pulse has moved, that must be, so one has to look at these with a moving coordinate system rather than a stationary coordinate system. So, that is the only difference here. You can see the only change when the pulse moves through a capillary at uniform velocity u bar. Pulse moves through the capillary. So, not a porous medium as such, we have gone up to a capillary. So, let us, so with this understanding, suppose now we are looking at a situation where we have a pulse going through a capillary, not a porous medium. So, if it is flowing through a capillary of cross sectional area A, so here it is just open capillary, no, not a porous medium. So, if we give a pulse, so the center of the pulse is here. Now, the center of pulse is shifting, and the center of pulse after residence time is given, the center of pulse will reach at the outlet. So, if this is so, then one has to work with a moving coordinate system, because Z has to be calculated. See, mind it, here the concentration is changing with time. So, the change with time with reference to this Z. But if the center is continuously moving instead of a static system, so all the Z that you calculate now, when the center is here, the Z has to be calculated with reference to that center. So, accordingly, here is a correction made, that when it is moving, Z minus u bar t. You see, it makes perfect sense, because it is at after time t, this center will shift from this point to a location which is equal to this center will go up to a distance u bar into t after time t. So, your center is here. So, all the Z value that you are looking at, that Z value has to be with reference to Z. Say, let us say I am looking at, this is my new Z. So, first thing you have to do is subtract u bar t from that Z. So, then you are talking about Z with reference to this. So, this correction has to be done with Z. So, we are talking about a moving coordinate system. So, this, when a pulse moves through a capillary, these must be taken into account, particularly this part. So, when the velocity profile becomes non-uniform, the governing equation changes along with the boundary conditions. What does this mean? Here we are assuming that as if this front that is traveling, suppose I have a pulse that is traveling, we have as if we have this entire fluid is flowing at a velocity u bar. Okay, so then it is all right, but in many situations it is not exactly moving at a velocity u bar, rather one can see a parabolic velocity profile like this. So, in that case, if there is a parabolic velocity profile, then the pulse that you have given, the pulse will also be stretched in a parabolic velocity profile like this. And parabolic velocity profile is common. We have already seen for a flow through a pipe, for laminar flow through a pipe, one ends up with that functional form we have seen, 1 minus r by capital R whole square. That is a parabolic form, right. So, now this is, so this pulse will be stretched like this. So, this is where we have higher concentration, and so now earlier what we were thinking, that if there is a single front like this, if there is a straight front like this, so as if this was the center of the pulse and this is how it is diffusing. So, it can diffuse to this direction and this direction, and then we had a governing equation by taking a differential dz, and then volume we calculated a dz, and in minus out accumulation and fixed second law, and all those things we had done already. But here in this case, if this pulse itself is stretched like this because of the parabolic velocity profile, then we will see that diffusion is taking place in this direction, here in this direction, here in this direction, here in this direction. So, it is I mean, it is creating a slug, and it is a completely different ballgame. So, this is something. So what we said is, when the velocity profile becomes non-uniform, that means you do not have a single velocity existing everywhere all along the cross section, then the governing equation changes along with the boundary conditions. So, if had it been a standard flat front, this equation could have been just fine. So, with this understanding, if we try to look at what we mean by a parabolic velocity profile, we would like to look at something which is, first of all, let me tell you that for a capillary, this particular phenomena is known as Taylor dispersion. That dispersion we are talking about, first of all we said diffusion in a static system, then we are trying to extend it for a flow system. So, moment we consider diffusion plus flow, that will be called dispersion. Okay. So, we have already given an equation, we have just extended the static case only with a correction on z. We said instead of a fixed coordinate, we are going to a moving coordinate. So, z minus u bar t, instead of z square term, we now have z minus u bar t whole square. So, dispersion has already started there, but now we have said here that it could very well be that the front may not be uniform, and non-uniform in the sense the front could be parabolic. We have already seen that it could be the velocity profile could take a parabolic form. In fact, that is what we have seen in the flow equations, where when we defined friction factor, at that time we looked at the velocity. If we look at the velocity profile, it is basically 2 average into average velocity into 1 minus r small r by capital R whole square. So, that itself means that it is parabolic. So, if one has this kind of parabolic velocity profile, and if one wants to know what is the concentration profile, so this is provided by Taylor. So, it is referred as Taylor dispersion. In this case, first of all, here we let us say we pick up a washer shaped object. Let us say this is the pipe, this is the capillary, this is the capillary, this is the capillary with radius r0. Okay. Out of that we pick up an annular area. Annular area is given by this blue dots. This annular area we are talking about, and this annular area is between, inner radius is r and outer radius is r plus dr. This width is dr, and it has in the direction of flow, this is the direction z in which the flow is taking place. Let us say this annular shaped area we have taken, this washer shaped area, it has this thickness of dz. So, if we try to do this, so z is in this direction in which the flow is taking place. So, if with certain assumptions, we will get into the assumptions in a moment, if somebody does the mass balance equation in the same way as we have done fixed second law, we have already seen that this del C1 del T is equal to d del square C1 del z square for a one dimensional system. If one extends this to a cylindrical system, RZ system, okay. So, we have r in this direction for a capillary, r is the radial distance and z is the along the center, this is along the center line, the z is put here. So, then in that case this right hand side will have, instead of this is for a Cartesian system, one dimensional Cartesian system, but when you go for RZ system, so you are considering the diffusion in r direction. So, that means d by r del r of r del c del r, this is diffusion in r direction, in r direction. And further you have, this is arising from the convection, that means there is some material that is being delivered because of the velocity itself. So, that is by convection. So, what are these terms? Let us look at quickly. We are considering, we said that the Taylor dispersion was supposed to simulate this case of parabolic velocity profile and a pulse is getting stretched. The pulse is getting stretched like this. Okay, so this is the pulse. So, we are interested in, we are saying that the diffusion can take place in these directions. So, this direction is basically r direction, because basically this is r and this is z. So, you have assumed that as if the diffusion, so if we pick up this, when we work with this differential element, we have a diffusion that is taking place in this direction and this direction, that means in r direction, but in z direction there is no diffusion, that is one thing. So, you are assuming, first of all, this, when we worked with the earlier case, there the diffusion was only taking place in z direction, there is no scope for diffusion in r direction because the velocity profile is all flat. So, that time the slug was all straight, slug was not stretched. But in this case, to simplify, what Taylor did is, Taylor said in this case diffusion in z direction for the time being you ignore. Later on Aris has shown that okay, the axial diffusion can also be included in these, and then the solution, what would be the solution, that has been found out. But okay, for the time being, when Taylor has arrived at the first equation, Taylor assumed that axial diffusion, that means this in the z direction, that diffusion is ignored, only the diffusion in r direction is included. So, this is the diffusion in r direction Taylor has taken into account. And second thing is, the fluid is being delivered here in this case by convection. What is convection? Suppose I have a differential element and I pick up a differential element, there could always be diffusion in the r direction. Okay. So, the minus d del c del z one, something will go out this way, that is a diffusive process. But since the flow is taking place in this direction, so naturally this velocity v will carry some amount of solute with it, and some amount of solute will leave the differential element with the flow. So, if these are not same, so in that case there will be an accumulation arising from these, and that will contribute to this del C1 del T. So, that is exactly this term, okay, because V is a velocity term, V is in meter per second. So, if we write V into area, cross sectional, the area of the differential element, so that would be then so what is the cross sectional area anyway? We can very well calculate. The cross sectional area of this washer shaped element is 2 pi r dr, right. So, 2 pi r dr, v at a particular z. Okay. So, this gives me, this is the velocity in meter per second, 2 pi r dr is the cross sectional area of this annulus. So, this product gives me meter per second into meter square, that means meter cube per second. Meter cube per second, and if you multiply this with C1, this gives me meter cube per second into kg per meter cube. So, this gives me kg per second. Mind it. So, there is always some kg per second going in. If you multiply by delta t, so many kg is going in. And what is coming out from this? The one that is coming out, this is in. This is in. And what is out? Out would be V at z plus. This C1 is also we are looking at C1 as a function of R and Z. So, similarly here also V as a function of R and Z. So, this is V as a function of R and Z. Here also V as a function of R and Z plus delta Z, that is going out. Similarly, you have 2 pi r dr C1 at Z R and Z plus delta Z. So, this is out. So, this in minus out, this also one has to consider alongside this diffusion and accumulation. So, this has been considered, and the velocity is written as 2 into average velocity into 1 minus r by capital R0 whole square. So, this whole thing is the velocity term. Basically, this is the V. Okay, this is the V, and here we are having a minus sign, because here in this case the del C del R itself had a minus sign, mind it, the flux, but here we do not have that minus sign to start with. So, that is why you are ending up with a minus sign here. So, this is V del C1 del Z, this term will come here, I mean it has to happen, V del C del Z has to come, because this in minus out has to be accounted, and this is the diffusion in R direction. So, one has to solve this equation. So, what Taylor has done is Taylor has solved this equation, and Taylor has used these boundary conditions that at t is equal to 0 for all z, at t equal to 0, that means time when you start, this is a Dirac delta function, m by this is a Dirac function m by pi r, this m by a, instead of a you can write pi r naught square, that is the area. Okay, that is the cross sectional area. And for t greater than 0, there are two conditions one has to satisfy. One is r is equal to r0, that means at the wall of this capillary, r is equal to r0, there is no flow possible. Okay, no flux, nothing. So, d del C1 del r minus d del C1 del r equal to 0, no flux. So, that is why simplified it is del C1 del r equal to 0, no flow. And for t greater than 0 at r equal to 0, intuitively we can see there has to be some symmetry existing, because everything that is happening there, there has to be some kind of symmetry at r equal to 0. For example, if I mean to start with the velocity profile, I can see that if we work with the upper part, we can ignore the lower part. So, there has to exist a symmetry at r equal to 0. So, if there is a symmetry, then del C1 del r has to be equal to 0. So, these are the conditions, initial condition and these two boundary conditions, and this is the governing equation Taylor had to work with. So, to work with this kind of a stretched pulse. So, Taylor said that if there is a flow through a capillary, one has to consider this stretching, and the one has to consider these dynamics will be completely different. And in porous medium, basically these are capillaries of size 1 micrometer. So, naturally this type of dispersion will be extremely important. So, that is so now let us I am going to close this lecture here. In the next lecture I would be continuing. So, you have to remember this equation and the contribution of individual terms, and we will continue from here, and we will see, because the aim of the Taylor was to arrive at the same form of equation that we had worked with earlier, e to the power minus z square. That same form of equation Taylor wanted to arrive at, so that the situations can be compared with reference to a static system. So, let us see what Taylor has done as a solution. So, this is the governing equation that I mentioned, the boundary conditions that I mentioned just now, and then Taylor had worked with these scheme of things to find out how the dispersion will get modified, how the dispersion will change if instead of a plug flow, instead of a uniform velocity front, if you bring in the parabolic velocity profile, which has to happen if there is a laminar flow in a capillary. So, I am closing this lecture here. I will continue this exercise in the next lecture. Thank you very much.